If you remember from the last lecture, we discussed how a rate law can be calculated using the method of initial rates. This method was crucial in determining the rate constant as well as the orders of the respective reactants. The rate law we've been working with is really the most basic form of a rate law. It's more accurately called the differential rate law. However, sometimes it is more useful to pull apart the different variables in this equation so that the unit of time might be assessed. If you look at the differential rate law that we've been discussing, it looks like this. As you can see, the rate is there, the K is there, and we're going to talk a little bit more about that later. The reactant concentrations are there, and their exponential relationship is expressed in the orders. Unfortunately, there's nothing in that law that allows you to input a certain amount of time. This means that you have no way of directly assessing how much concentration will remain after a given amount of time. This may not sound that important, but without it, scientists would not be able to assess any point in a reaction except the beginning and the end. If you look more carefully at these variables, though, you will see that time is hidden within the units of rate. Remember when we were describing a rate law and we were calculating it using the method of initial rates? The rates were always given in the following units: mole per liter times some unit of time. We often use the second, or some variation of that. This means that the unit of time is incorporated into the rate. In order to access it, we can employ the calculus principle of integrating the rate law. Don't worry though, you won't be expected to perform this calculation each and every time. Please understand though that the application of calculus to the differential rate law is what renders a new form of the rate law that allows us to incorporate time into our calculations. The interesting thing about this is that while the differential rate law appeared in the same format for all possible orders, the integrated rate law appears in a slightly different format depending on the order of the overall reaction. This is because different overall orders come from having different exponents and therefore slightly different relationships with the rate. Let's take a look at a first order reaction. First of all, there are a couple possible ways of making this happen. Okay. The first way of having a first order reaction is this: one reactant that decomposes into products in which the relationship between the concentration of that only reactant and the rate is 1. This is going to give you a rate law that looks like this. Rate equals K, A to its order, and the order would have to equal 1. Another possible example, or another possible way of having this of an overall order of 1, is if you have a reaction like this one, but the concentration of B has no effect on the reaction rate. So its particular order would be 0. This leaves you with a rate law that looks like this. Rate equals K times the concentration of A, which would be raised to the first order, times the concentration of B raised to the 0, which really can be simplified down into rate equals K, A to the first. Okay. However, when we discuss rate laws, and especially the integrated rate law, we really only talk about the first case. We really only talk about this most simple case up here. So, if we take this particular case with that rate law, okay, we can look at it as rate being equal to the change in concentration of just A over the change in time. Like we just said, though, the rate also equals K times the concentration of A. Because the rate of the reaction equals both of these, we can set them equal to each other. Okay. This gives us an overall reaction of negative change in the concentration of A over the change in time equals K times the A. Integrating this, applying the calculus, renders us the first order rate equation that looks like this. Okay. A similar method can be used to assess a second order overall reaction, which would essentially be the rate equals K, so if we're talking about the second order reaction, we're assuming we're starting with a simple rate equals K A squared. There are other possible ways of getting a second order overall reaction, but this is the one that we're discussing now. Okay, so a second order reaction would look like this once it's integrated. The last order that you'll need to know is the zero order. If you apply all of these same concepts to the zero order equation, which in the differential form would essentially be rate equals K, okay, you're going to get an integrated form that looks like this. If you look at all three of these equations written in this format, see we've got first order, second order, and zero order. Okay. You can see that they all generally follow the format of y equals mx plus b. In all cases, t is the x-axis, x right there, and the y-axis actually is going to change depending on what the order is. Additionally, the slope, which is the k, has units that are sometimes negative and sometimes positive, and its units are going to change depending on the overall order because of that changing y-axis. For a first order reaction, the units for K are 1 over time. For a second order reaction, the units for K are liters per mole times time. Okay. For a zero order reaction, the units for K are moles per liter times, let's get a times to show up, time. Okay. Additionally, this new integrated format of the rate law increases the range of questions we are able to answer with this concept. For example, if you have a sample of hydrogen peroxide, you know that it naturally decomposes over time. If we know the K value and the initial concentration, using an integrated rate law, we would be able to determine the concentration of that sample at any given time, as long as we know whether it is a first, second, or zero order reaction. Okay. This means that the trick is discovering which order a reaction is. When we were only working with the differential rate law, we calculated the respective orders, and therefore that overall order, using the method of initial rates. The best way to determine the order of a reaction using data from the perspective of the integrated rate law is by graphing it. Okay. And if you look at the reactions or the equations that we have up here, you can see how they're going to have slight differences in their graphs. A first order reaction, for example, while it is y equals mx plus b, is only going to be linear. It's only going to fit that y equals mx plus b format if the data is done as the natural log of the concentration graphed versus time. And as you can see, it's going to be a negative slope. If we look at a second order reaction, we can see that we're only going to get a linear fit if we graph the 1 over the concentration of A versus time. And this is going to be a positive slope. And if we look at the third one, we can see that the only way to get a linear fit is if we graph simply the concentration of A versus time. Okay? And again, this one's going to be a negative slope. Okay? So by graphing the data and seeing which of these graphs it happens to fit, we can determine whether it's a first order, a second order, or a zero order reaction. Okay. Usually the data for this type of problem will be given as concentration versus time. Okay. Here's an example. So we have an overall reaction. We don't necessarily know what its order is going to be, but this nitrogen dioxide has decomposed over time, and at these different time intervals, concentration values were taken. So just looking at this, it really is impossible to tell what its order is. Graphing it, however, will allow us to determine which y-axis will also give us a linear fit. Okay. Remember, for a first order reaction, the y-axis has to be natural log of concentration. For a second order, the y-axis is 1 over the concentration. And for a zero order, the y-axis is simply going to be the concentration. Whichever y-axis renders us a linear fit will determine what our overall order happens to be. Watch the next video to see an example of how this would work.